Just about everyone uses some type of disposable battery. And while they may not look like much, every battery is like a tiny power plant, with over a dozen parts working together to generate electricity, practically out of thin air. Here at the Rayovac factory in Fenimore, Wisconsin, they pump out 3 million of these mini miracles in various sizes every day. The only real difference between AAA, AA, C, and D-sized batteries is that the larger batteries hold more ingredients and in turn perform longer in similar devices. They all deliver the same 1.5 volts of electricity. The basic components of a battery include a can, which houses all the ingredients, the cathode, or positively charged part of the battery, the anode, or negatively charged materials, and a paper separator that fits in between the cathode and the anode, ensuring they don't touch one another. The cathode is the first part to go into the battery, and it's made up of manganese dioxide and graphite. A worker loads 4,000-pound sacks of these materials onto platforms and empties them into hoppers. Hydraulic arms massage the bags to empty every last bit. The materials then travel through these pipes and into the cathode mix area, where computers direct valves to disperse the correct amounts of each into a mixer. The resulting powder, called cathode mix, travels through bucket conveyors into the next room, the cathode press area. Here, a turntable-style forming machine presses the fine gray powder into these round, hollow pellets. Meanwhile, nickel-plated steel battery cans made outside the factory feed into the other side of the line. They travel single file through a series of conveyors until they meet up with the cathode pellets. Here, mechanical feet push 3 cathode pellets into each can. With the cathodes in place, these cans shoot up a magnetic conveyor and travel into the next room to the D line. Here, they'll officially turn into D batteries. The next ingredient is simple but crucial. Without it, the batteries would all short out. It's paper. A paper cylinder is inserted on the inside of the cathode, and then an additional paper button is pushed down into the bottom of the can, creating a sort of paper cup inside the cathode. The paper acts as a physical barrier between the positive ions in the cathode and the negative ions in the anode to keep them from interacting with one another before the battery is plugged into a device. If you look closely, you can see one machine curling the paper into individual cylinders. And the next machine pushing buttons down into each can. Now, the batteries have their paper separators in place, but they're still not ready to be filled with negative ions. They need one more ingredient. This is potassium hydroxide, a synthetic chemical compound that's highly corrosive, but instrumental in making batteries function. It pumps directly into nozzles in the D line, that spritz 10 batteries at once as they go by. The potassium hydroxide is an electrolyte, meaning it helps conduct electricity in the battery. After they get their electrolyte, the cans then take a leisurely 15-minute ride to their next stop, giving the liquid time to fully soak in. Now, the batteries are ready to get their negative ions. These come in the form of a thick silvery gel called anode. This mixer churns zinc powder together with a gelling agent and more electrolyte. Then the mixture releases the resulting slurry into tubs by the ton. Before the mix goes into the batteries, a worker tests it to make sure it has the correct viscosity or thickness. If the mixture is too thick, it won't pump properly through the machinery and could stall the entire production process. Then the anode makes its way to the D line. Here, white nozzles squirt the silvery gel into the paper cup in each can. And then, the cans are ready for the next crucial part, the welded collector assembly. It's basically a nail welded to a steel end cap. When the battery is connected to a conductor in a device, the nail collects the electrons in the anode, sends them out through the device, and back into the positive end of the battery. The flow of electrons through the device gives it power. A machine makes the nails for the collector assembly from scratch in a separate area of the factory. Here, one long coil of tin-plated brass wire feeds into this heading machine. Inside, a blade cuts the wire into 1 1/4-inch strands. Then, what's known as a cold header grinds the end of each piece into a nail head. The finished nails pour out the other end into buckets and then make their way down a conveyor. The belt drops them off into this rotary vibrator. Inside, the pins bump up against one another, removing any burrs or rough spots. The nails empty out into bins, which then make their way to the collector assembly line. Here, the nails enter the line and move single file to meet up with the end caps. An automated welder seals the pins to the end caps. And a magnetic conveyor sucks up the completed collector assemblies and sends them directly over to the D line. Here, they're inserted into the batteries. With their collector assemblies in place, the batteries are nearly finished, so it's time for a test. Coming up, we'll see if these batteries have what it takes to produce some power. And later, find out what this bike and this bomber have in common. Now that machines at Rayovac have filled these batteries with all their ingredients, it's time to put them to the test. Every battery feeds through this rotary tester, which quickly zaps it to make sure the voltage and amperage are correct. Any batteries that don't pass the test get knocked off the line by air jets. An automatic palletizer pushes the approved batteries into bins, where they head to the next stop. Aging. The batteries have to hang out for a while to allow the chemicals to settle. How long? That's one of Rayovac's closely guarded trade secrets. While the unfinished batteries age, a steel stamping press prints out the positive end caps that will soon be welded on the end of each battery. The end caps start out as one 4,000-pound coil of steel. The steel feeds off a spool into a 50-ton press. The press runs at 400 strokes per minute, stamping out 6 caps with every stroke. The caps exit the machine in that familiar shape, the positive end of a battery. The leftover scraps of steel make their way on this conveyor to another part of the plant to be bundled up and sold as scrap metal. While the positive end caps shoot out into bins by the thousands and make their way to the labeling line. As the end caps feed into the line, batteries that have finished aging enter the line to meet up with them. A welding machine fuses an end cap onto the positive side of each battery. Now, these are really starting to look like D batteries. But they're still missing one important part: the labels. Labels aren't just for decoration. They insulate the conductive surface of the battery can so that nothing can touch it and short out the battery. Now the batteries have their labels, but the ends are sticking straight out. So they pass through this 200-degree heat tunnel, which shrinks the labels to a tight fit. And finally, these are completed D batteries, ready to be wrapped up and sent out for use in a battery-operated device near you.